I've done traveling on trains, and I've often marveled at the streamlined comforts and conveniences they offer for passenger travel, at their speed and general reliability. And watching freight trains go by, I've often wondered at them, too. At the way cars from all railroads are likely to be found in the trains of any railroad, and where the cars come from, and what they haul, and where they're going, and a lot of other things. Nation's big freight job. Hardly more than a century ago, over dusty trails or dirt roads, passengers and freight moved on horseback or in covered wagons. Then came a new kind of transportation, the railroads. Here was the real beginning of America's greatness, of her expansion and development in mining, agriculture, and industry. Here was the economic foundation upon which our nation was to build. Well, that's the assignment the editor gave me, to get the story behind the story of modern railroading. And I'm glad he did, because it gave me a chance to go backstage for a close look behind the scenes of railroading, to find out just how railroads became the great transportation system of today. And here's a part of the story as I found it, in the words of the men doing the research that's back of the tremendous advances railroads have made through the years.
Yes, the railroads are always looking for better things and for better ways of doing things. Their story of unending research, invention, and ingenuity began with the beginning of railroads and goes on today as never before. My work is on the campus of the Illinois Institute of Technology in Chicago, in the Central Research Laboratory of the Association of American Railroads, nerve center of the widespread job of railroad research. We do collectively things which can be done more efficiently and economically than by railroads individually, so that the traveling and shipping public can have faster, safer, more economical service. This job of research is of vital importance in the constant effort to improve everything it takes to run a railroad. Consider the very foundation of railroading, for example, the track over which trains operate.
To the naked eye, it looks pretty much the same as it did years ago. But through research, every part from the rail to the ballast and even the subgrade beneath the track has been made better. Rail itself is heavier and stronger today to keep pace with the constantly growing loads it supports. It got that way through years of testing in laboratories and out along the track under conditions. America's 225,000 miles of railroad is available to try out under test conditions new ways of construction, new types of equipment, new methods of railroad operation, making this the biggest proving ground in the world. Research and experience have led to better design and improved metallurgy, so that today's rail has a service life 50% greater than that of 30 years ago. Track as a whole is kept in condition by machines and methods that have revolutionized maintenance of way work. Men working on track today have the use of machines that often resemble weird contraptions out of a dream. Equipment such as this has lifted much of the heavy work from men's shoulders, at the same time getting more and better work done at less cost. This ballast cleaner, for instance. Mechanical hands methodically scoop up the dirty ballast to be carried by continuous belt up into the mechanism where it is cleaned. The ballast then emerges as good as new and is replaced in an operation that is now completely mechanical. But to do its job, ballast must be packed under and around the cross ties. Research and testing have brought about the development of extremely effective ballast tampers. Metal fingers hammer the ballast to ensure smooth, even riding by establishing firm foundations for ties and rails. Still another result of prolonged research has been the development of the rail detector car. Mounted on the underside of each unit, directly over the rail, are powerful electric magnets, which locate any possible internal defects in the rail. When a defect is spotted, the exact location is marked for immediate rail replacement. But what the railroads are doing to improve and maintain track through research is just part of the overall story. Another part, just as vital, is that of the vast changes being made in the equipment rolling over the track.
From the days of the little old teapot engines of early railroads to the giant locomotives of today, there's been steady progress in railroad motive power. Steam, electric, diesel, turbine-powered engines, and perhaps tomorrow, even atomic power. But to me, the steam locomotive has always represented the adventure and romance of early American history. And the steam locomotive is still on the job, an important factor in providing low-cost, dependable transportation. But the development of the diesel-electric locomotive has become one of the most important steps in railroad progress. I was surprised to find out that the first diesel locomotive capable of pulling a freight train at today's required speed went into service as recently as 1941. That was a great step in the most rapid changeover in motive power history. For today's diesels perform about 3/4 of all railroad transportation services. When I checked into the why and wherefore of this great changeover, the answer first and foremost was cutting down operating costs with greatly increased efficiency. I found that the diesel burns less fuel, can start heavier loads, can pull them at higher sustained speeds, and needs fewer repairs. The development of the steam, diesel, electric, and now the gas turbine locomotive is a good example of how the railroad industry adapts and applies to its own needs the results of the research of related industries. Exciting or romantic about the railroad freight car, and yet without it, the America we know could never have come into being. For the freight car is the moving element in the world's greatest assembly line, railroads, carrying the raw products and manufactured commodities of a whole continent, the veritable lifeline of a nation.
Carrying more tons of freight, more miles than all other forms of transportation combined. That's the day-by-day record of America's premier mechanized workhorse, the modern railroad freight car. It, too, is a product of study and experimentation. Much of this experimentation, like testing any other mechanical device designed for railroad use, cannot be confined to the four walls of a laboratory. So railroads and manufacturers have cooperated in operating complete trains, rolling laboratories for road tests, carried out under actual operating conditions, sometimes at speeds as high as 100 miles an hour and more. Here's one such laboratory train with which the railroads test high-speed freight car wheels and trucks designed to lessen vibration and increase stability. Another working part in which great progress has been made is in braking, or the power to stop. I've had an opportunity to visit the laboratories and see these testing dynamometers in action. This combination of testing in the laboratory and on the road is practical research at its best, trying out different kinds of brakes under all conditions, all with a view of ensuring the safest, most comfortable rail service for the traveler and the most dependable and economical service for the shipper. The AAR Draft Gear Laboratory. Here's a specially designed machine for drop testing draft gear, those vital parts behind car couplers which cushion and protect the car and its contents against stress and strain. That's a 27,000-pound weight you're looking at. simulating conditions far more severe than would normally be found in actual service, it's dropped from different heights on the draft gear under test. The one thing we freight men know above everything else is that a damaged shipment means financial loss to everyone concerned. And conversely, better packaging, loading, and handling spell more dollars in the pockets of shippers, carriers, and receivers alike.
Concentrated inquiry into the science of packaging, breakage, loading. That's part of the everyday program at the Central Research Lab in Chicago. What happens to lading inside freight cars during switching operations while in transit? These are some of the questions that have led to extensive railroad research in damage prevention. And out of this research have emerged new methods of practice and usage to be adopted on an industry-wide basis. Coupling tests tell us what we try to find out about impact effect on lading and how better to build cars to cushion the shocks of movement. And railroads do something about the weather, too. Some of the earliest uses of artificial refrigeration were in the movement of perishable products to market. And today, the aim of our research is to keep on improving the methods which help to deliver fresh fruits, vegetables, meats, dairy products, all kinds of perishables to all parts of the country and get them there fresh as the day they were picked. This means constant experimenting and testing by our refrigeration engineers and technicians in the search for lighter, more efficient insulation. And again, our work leaves the lab and is carried forward in transit. Here's a string of refrigerator cars being prepared for a cross-country test. Wiring and special recording mechanisms installed. On the trip, temperature and other conditions carefully recorded for later analysis with the view to improvement of car design, insulation, forced air ventilation and circulation, heat and water vapor transmission through the insulation. All to the end that the railroads can go on doing an even better job of supplying every part of the nation with fresh, healthful foods the year round. An innovation in the handling of perishables in transit. Complete mechanization of icing and re-icing. Self-propelled units servicing 2 lines of cars at one time under one-man control, thus cutting down train delays at re-icing stations.
Getting the most out of trains and tracks calls for many things, like, for instance, communications and signals. Railroad signals have come a long way from the time when a colored ball hoisted to the top of a pole signaled that the track ahead was clear. Under the world's most complete, most effective, and safest system of traffic control. Basic in this traffic control is the automatic block signal system, by means of which a train in a block or section of track reports its presence to all approaching trains. This is done automatically through electronic operation of signals, which tell the engineers of other trains whether to stop, to proceed with caution, or to go ahead at authorized speed. On sections of line equipped with centralized traffic control, all trains automatically report their exact position and movements through lights on a map on a central control board. Simply by moving little levers on this board, the operator you see here can set signals and throw switches that govern the movement of trains as far as 200 miles away. Through his control board, he lines up signals and switches which are so interlocked as to make it impossible to set up conflicting routes. special devices are also being used to control the movement of cars in busy yards and terminals, the places where trains are made up or reclassified, the hearts that pump the flow of commerce out across the nation. Here in a push-button yard, a locomotive shoves the cars of an incoming freight up to the top of the hump. There, the cars are uncoupled, singly or in groups, and the force of gravity takes charge. Gravity controlled by the twin marvels of electronics and pneumatics. As the cars roll downhill, their speed is governed by car retarders, whose slowing down pressure against the wheels is adjusted from a control board in a tower. As the cars roll on, they are routed into their proper tracks by switches which are thrown through push-button controls. Two-way radio communication connects all parts of the yard with the control tower to further speed up the movement of cars through great terminals. These great car interchange centers point up dramatically the importance of another product of railroad research, the standardization of working parts, which makes it possible for any freight car of any railroad to be operated in the trains of any other railroad. That fact is at the foundation of our continent-wide flow of commerce. And it is but one of the results of railroad research in better cars and locomotives, better signals and communications, better tracks and terminals, and the better methods of railing which, combined, explain why today's freight trains turn out 3 times as much transportation service in an hour as the average train of 30 years ago. Well, my story is just about finished, but the railroad story itself goes on, being written day by day in laboratories and shops and out along the tracks of individual railroads working together through the Association of American Railroads. Still other chapters are being written in university and commercial labs and within the industries that supply the railroads. As a reporter, I came away with this guiding idea, that in the railroad industry, the innovation of yesterday is the commonplace of today, and that the best of today is not good enough for tomorrow. This is the creed of the Railroad Research Program, the heart of railroad service to the American traveler and shipper.